Welcome to the Problems Channel Season 3, Episode 32, the episode which I titled Hyperbolically Speaking because the title of this episode is a hint. And before we deep dive into the underlying mathematics of the next challenge, as a friendly and a traditional reminder, if you're joining our channel mid-season, especially after Season 1 and Season 2, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel. And welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you. Use the comment section under that episode and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel. In the mathematical problem S3E32, we are asked to evaluate an indefinite integral that you see in the upper left corner of your screen in at least two creative ways. And in this case, the integration is carried out all with the field of real numbers, which is to say that the numbers x and a are strictly real. That is correct. You heard it from a person who received both the Fields Medal and the Abel's Prize, perhaps the most two highest honors a person can achieve in mathematics, aside from an organic recognition by fellow mathematicians. The moment we engage in a raw symbolic manipulation, we stop thinking about the meaning of the symbols that we're shuffling at the moment, and perhaps nowhere else this idea shines as brightly as in integral calculus, because quite often when I see how especially the younger students of mathematics jump head over heels into the underlying evaluation of this or that integral, I quite often wonder if I yank the student out of the crowd and ask that student, why did you undertake this specific path or this specific computation? Then the chances are high that that person will not be able to motivate his or her actions. And on this channel, I keep advertising the idea that mathematics, first and foremost, is an art of telling a story, and that is true, but in a certain sense, this is a higher art, a higher skill, because at its core, the kernel of mathematics, so to speak, is the process of generating and regenerating and combining and recombining ideas, whether we can splice or weave these ideas into a coherent, beautiful, crisp, and elegant story is a different matter altogether. Most people, or a lot of people, simply cannot do that, and that is why we dedicate so much time to that art on this channel. But stepping back a little bit and concentrating on the process of generating and regenerating and combining and recombining ideas behind every symbolic manipulation. It doesn't really matter which area of mathematics that is. It could be a theory of graphs, theory of groups, it could be linear algebra, it could be analytic geometry, integral calculus, differential calculus, on and on and on. There's always sits a sound mathematical idea, and when we generate that idea, we think like a mathematician. As such, coming back to our integral, when our integral, let's say in general, is a function that is rational in the symbol x and a square root of a quadratic expression, then one way to evaluate the underlying integrals is to generate the following clever or creative idea. Here we step from the underlying algebra into geometry and to our square root of a quadratic expression taken with the plus or minus sign. We correlate the variable way, the proverbial function, and you see in algebra plus and minus is just plus and minus, but once we step into the underlying geometry, we see that the plus and the minus, or the sign in front of the square root, geometrically correspond to the upper half plane or the lower half plane, depending on the sign. The plus sign corresponds to the upper half plane, the minus sign corresponds to the lower half plane of the graph, or a portion of a graph that is represented by these here symbols. So now we will engage into a certain amount of raw symbolic manipulation, symbolic shuffling, but there is an idea behind this manipulation, and the idea is to try to come up with a mechanism that will guarantee, in some sense, or come up with an industrial strength method that will allow us to always get rid of irrationality and wipe this square root or radical free from the integrand. And to that end, we square both sides of this relation. We wipe out the plus or minus sign, so we get this expression over here. We will mark it as the equation number 1. And here's a series of 1-2 punch clever ideas. First, again, we switch from the algebra to the underlying geometry, and on the corresponding curve, and in analytic geometry, it will be shown that this here expression that we obtained on this step after squaring this relation shown over here, y squared equals alpha x squared and so on, represents the so-called curve of order 2, or a quadratic curve, and all such quadratic curves in more details can be classified into ellipses, circles, parabolas, hyperbolas, and straight lines in a degenerate case, which we exclude. So for now, we will take it that this here expression represents a generic quadratic curve and not a straight line. So as the first clever idea, we pick a point P0 on that curve. And again, switching back from geometry into algebra, we say that algebraically, the fact that a point belongs to a graph of a certain function means that the corresponding symbols, when inserted into the corresponding expression, will form an expression that is true. And this is what we obtain over here. If we inject the points, the coordinates x0 and y0 into equation number 1, this is the equation that we get. Y squared 0 equals alpha x squared 0, and so on. We will mark it as the equation number 2. Next comes the second clever idea, and this idea is the following. It is based on a remarkable property of each and every non-degenerate quadratic curve to have at most 2 points in common with the straight line. So the overall possibilities are 0 points in common, 1 point in common, and 2 points in common. And when such a second is formed, we already know, again, whether it be our high school mathematics or early course in college, the equation of a straight line that passes through the point with the coordinates x0 and y0 is shown over here. And the meaning, look at this, this is another thing that goes back to the quote that you just read. The meaning of the symbol t becomes evident. What is t? T is the angular coefficient or the slope of a straight line, which is a quantity that is numerically equal to the value of the trigonometric function of tangent evaluated at the angle that is formed by the positive branch of the underlying Cartesian coordinate system and the corresponding straight line. And again, if we rewrite this expression shown over here by moving the y0 component of the point that sits on the corresponding curve to the right hand side of the equal sign, this is the expression that we obtain. And now what remains is what mathematicians call a finite computation. We simply inject the right hand side copy of y into our expression shown over here in the equation 1, and this is what we get. We simply move the expression shown over here down, square it, and equate it to what we have on the right hand side of the equation 1. This is a very straightforward maneuver. Next, we open up the parentheses, square of the first term plus twice the product of the first and the second term plus the square of the second term, t squared x minus x0 squared, and the same thing on the right hand side without any change. Now comes another interesting maneuver. Look at this. We have over here on the left hand side the square of the y0 component of the point that we picked on our curve, and I will talk about how we picked that point in a few seconds. But now we go back to the equation number 2. Look at this. We have the image of the square of y0 shown over here. We simply take this image from the right hand side and we put it into here. And what do we see? Well, look at this. We have our alpha x squared 0 plus we have beta x0 plus gamma. And what do we have on the right hand side from the equation number 1? We also have gamma. So gamma, one copy of gamma, and the second copy of gamma cancel out. Now we move everything that has to do with alpha to the right hand side of the equal sign, and everything that has to do with beta to the right hand side as well. Here we have only twice the product of the first and the second term left here, plus the square of the second term is equal to alpha here and alpha here, x squared minus x squared 0. You see, this is how we form this, and with the beta coefficient the same. X on the right hand side of the equal sign, x0 flies to the right hand side, gains the negative sign in front of it, is the same thing. But what do we see now? Well, due to the wonderful joy of the cancellation of the free floating term gamma, we now see that we have one copy of the difference x minus x0 present throughout the relation. Look at this, x minus x0, x minus x0 squared. Here we have the difference of squares, which is what? Which is the product of the difference and the sum. We have our difference and the difference over here. So once we cancel one copy of this, then we cancel square, square, and replace it with the plus sign. Then one copy of x minus x0 is gone, and this copy is gone. So what do we have? 2y0t plus the square of t times just the difference equals alpha x plus x0 plus beta. This is the equation number 3. Take a good look over here. This is a very straightforward manipulation. Again, yes, over here, as you can see, some people say, Roman, we are doing exactly what you criticized a few seconds ago. Mind-numbing symbolic shuffling, yes, but there is an idea, like I said, that motivated this symbolic manipulation. And look at the prize, look at what we get in return. So I rewrote this equation on top of the board on the right hand side of your screen. This is exactly the same thing, modulo the fact that I moved everything that belonged to x. Look at this, alpha x and then x t squared on the one side, on the left hand side of the equal sign. This is the manipulation that is quite straightforward, but here I carefully wrote on the right hand side the equation, the relation that shows the diminishing powers of t squared, t to the 0th with alpha x0 plus beta, and we're home free. Now we reap the benefit of this mind-numbing symbolic shuffling. We see that as a function of the parameter t, which, as we already understand it, it is the angular coefficient is a function that is rational in t, integral powers in the numerator of t, integral powers of t in the denominator, and this is the very embodiment of a rational function. But now look at the magic. Through the magic of this equation of the second, we obtained this equation, and look at this. I wrote it down for you one more time over here. We have a constant real number plus the first power of t times our rational function minus another constant real number, and this is also a snapshot or a recipe to manufacture yet another rational function in t, also a rational function in the variable t. So now we have that the coordinate of the second point, px, let's say we'll say that the coordinate of the point px y, which has the coordinates x, y, the coordinates y and x are what? These coordinates are rational, and it follows that we can use this substitution shown over here. Square root of our quadratic equation minus y0 equals t times the difference x minus x0 in order to always rationalize our integrand, no matter how complicated that integrand looks like, of course, provided that it is a rational function in x, the rational function in x, and the rational function in the square root of this quadratic expression over here. And by varying the parameter t accordingly, we can always make it so happen that the second point that belongs to both geometric objects at once, a second and our curve, paints or visits or travels the entire curve or a section of the curve as the need may be. And in order to show you some visual demonstration, I put together an animation using the free software called GeoGebra, where you will see that this is basically what I came up with is an equation of an ellipse in disguise. I picked this point over here, and then I animated the second point over here. So as this point traverses the curve, you will see that the corresponding second varies. Or you can also say that as I change the value of this angle over here, the point on the curve p x y traverses that curve accordingly. Please take a look. And the specific values of our constant real numbers, alpha, beta, and gamma, will dictate in which particular way we should pick our point P0 that has the coordinates x0 and y0. If the quadratic expression in the given integral shown over here has two real roots, lambda and mu, for example, then this algebraic fact finds its meaningful geometric interpretation in the fact that the corresponding graph of that function will intersect the x-axis of the appropriately chosen coordinate system precisely at the points lambda 0 and mu 0. I showed it over here, let's say lambda, and over here, let's say mu. And what does that mean? That means that if we go back to our universal, in some sense, substitution that, according to our theory, is guaranteed to rationalize the given integrand, then instead of the coordinate of the component y0, we put simply 0, and instead of x0, we can pick either one root or the other, so either the substitution square root of the whole thing is equal to t times x minus lambda, or t times x minus mu will always rationalize the given integrand. If, on the other hand, it so happened that in the given integrand the quadratic expression under the square root has the free-floating term gamma that is strictly greater than 0, that means over the field of real numbers there exists another real number to which we refer as the square root of gamma. And geometrically, what does that mean? Well, geometrically, that means that if we replace the value of the coordinate x here and x here under the square root, then we will have precisely the square root of gamma, and then plus or minus in front of that square root already tells us what? It tells us that the corresponding branch of the underlying graph of the function at hand will intersect the y-axis at a point that has the following coordinates: 0 for the x component, and then plus square root of gamma for the y component, or still 0 for the x component and then minus gamma for the y component, shown here and here. And if we go back to our universal substitution, then we see that instead of y0, we can pick what? We can pick, for example, plus or minus square root of gamma, and then instead of the difference x minus x0, the x component, the x0 component is 0, so for the point P we pick this or this. So here we will have simply x, and according to our little theory, this substitution will always rationalize the given integrand. Lastly, if in the given integrand the coefficient at the most senior power of x, or by the x squared, in our case this will be the constant real number, alpha, is strictly larger than 0, then again over the field of real numbers there exists yet another real number to which we refer as the square root of alpha. And in this case, when alpha is greater than 0, the underlying graph of the function will be what? It will be a hyperbola, which can be oriented in a number of different ways. For example, it's shown with the blue branches in the right half plane and left half plane, or with yellow branches in the upper half plane and lower half plane. In some sense, it doesn't really matter, because in this case, the asymptotes of such a hyperbola are shown over here. This will be the equation given symbolically or algebraically, if you will, analytically, plus minus square root of alpha right here, because we know that that number exists, times x. And the idea over here is that for the point P0, which has the components x0 and y0, which point would we pick? This is an opportunity for you to think like a mathematician. Meanwhile, a mathematician will pick over here the not a finite point, but the infinite point, or the so-called point at infinity that belongs to a branch of our hyperbola somewhere here, 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 or here, point at infinity on the hyperbola. And then what is the idea over here? We need to have 2 points that belong to the hyperbola. If one point is infinite that belongs to the hyperbola, then the idea here is to start intersecting our hyperbola with the straight lines that are parallel. You see, maybe I should pick which one? Maybe I should pick a red color. Intersect our hyperbola with the straight lines that are parallel to the asymptotes. You see, this is how we do it, this way or that way, and then consequently, for example, this way. We intersect our hyperbola with straight lines that are parallel to the asymptotes of this hyperbola. And these parallel straight lines, the straight lines that are parallel to the asymptotes, will pass through the point at infinity that belongs to the hyperbola, and the second point somewhere here, 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 and so on. This will be our proverbial point Px. And what is the equation of a straight line parallel to the given one. That will be y is equal to t plus minus square root of alpha times x. You see, this is the equation of a straight line parallel to an asymptote of a hyperbola. And in this case, we take that the components y0 and x0 in some sense are gone, and we only take the straight lines parallel to the asymptotes, and that means that in this case the substitution t plus minus square root of alpha times x, make sure that x is not under the square root. This substitution over here is guaranteed to rationalize the given integrand, provided of course that this integrand is rational in x, square root of a quadratic term. And the question is, okay, which way, how do you choose which substitution to go with? Well, the idea here is, again, this little theory that we developed together guarantees that under the given conditions in the shape of an if then Q implication, if we have a rational function yada yada, then it can always be rationalized. So this little bit of theory guarantees that we will be able to rationalize our integrand. The theory of integration of rational functions is very well developed. We consider if we can reduce a given, let's say, complicated problem to the theory of integration of rational functions, that we have one, we can always integrate the underlying material enclosed form as a finite combination of elementary functions. But the idea here is that sometimes perhaps even the simplest of integrals that contain such expressions, they can always be resolved. We know how to do it, we covered all the cases, but the underlying computations may be not so pleasant. But then again, the point over here that I'm trying to make in this episode is that make sure that whatever underlying computation or algebraic symbolic shuffling you undertake, this symbolic shuffling is born by a certain sound mathematical idea, and you generated this idea during the time when you were thinking like a mathematician. And in our case, we'll discuss it in a second, but to give you a heads up, in our case, what do we have? Our integrand looks as follows: x squared minus a squared, and then we know that in this case alpha is 1 is greater than 0, the whole thing applies. So we know that, for example, the substitution t minus x or t plus x will work. And how will you know which sign to pick? Well, in some sense it doesn't really matter much. If you pick the, let's say, the wrong sign, you should actually carry out the computations with the substitution t plus x and see what happens. And in the end, once you take the first derivative of the result, you will basically get the negative sign in front of your integrand, and that will be the branches of your hyperbola that live in the bottom half plane. With the substitution t minus x, we will get a function whose first derivative will be equal to precisely the square root of x squared minus a squared taken with the plus sign. And with a little bit of theory under our belt, we see that in our particular case, the given integrand corresponds to the hyperbola shown over here. This is the equation that is taken to be almost canonical, and I'll discuss this in a few seconds. We will spin this specific relationship creatively in the next segment in a few seconds. But geometrically, this integrand corresponds to two branches of this hyperbola, both of which lie in the upper half plane, and it means that our function is defined on the union of two subsets of real numbers from negative infinity to negative a inclusively, over here shown on the left, unionized with the subset of real numbers that goes from positive a inclusively to positive infinity that way. And you also understand why I named this episode the way I did, hyperbolically speaking, and there are two reasons for that. One of the reasons that you see right now, fundamentally we see that the substitution that will based on our theoretical idea, and theoretical reasoning always rationalize the given integrand, is based precisely on the idea that we're dealing with a hyperbola or a specific branch of it. We constructed, remember, the asymptotes, and then we started constructing straight lines parallel to asymptotes in such a way that they pass through the point at infinity on the hyperbola. And we understand the meaning of the parameter t. What is this parameter t? Well, the parameter t over here is basically a real number that offsets our straight lines parallel to the asymptote. In this case, what's the asymptote? Plus minus x, plus x minus x, and then the parameter t was simply a real number that moves this this parallel straight line parallel to the asymptote this way or that way, as the case may be. And I'm pretty sure some of our viewers who are more into algebra, even more into algebra than I am, they probably will be able to cook up a reason why in this case we have to take this one. Share your ideas with our community in the comments section. But now that we understand the geometry and the theory behind this here substitution, we already know that y is equal to t minus x. In other words, we know that the integrand itself without the first differential is already rationalizable that way. We do not even need to engage into any major symbolic shuffling, computing square of this minus this square root. None of that is needed. Look at this. We take this this relation, square both sides. Here there is no square root. Here is a trivial square root of the difference, t squared minus 2tx plus x squared and x squared. Look at this. Here and here cancel out. Move this guy to the left, this guy to the right. This is our result, x as a function of t. Look at this. Oh my, this is a rational function in t, just like our theory predicted. And from here, we instantly know the first differential of x in terms of the first differential of t. We can even compute this here result in our mind. We do not need the paper. u prime, the first derivative of the numerator, 2t times 2t is 4t squared, minus the first derivative of the denominator, 2 times the numerator itself. 4t squared minus 2t squared is 2t squared minus 2a squared. 2 in the numerator, 4 in the denominator cancel out. So this is our result times the first differential dt. Game essentially over. Look at this. Our wonderful, clever idea of rationalizing through the t minus x substitution. All we have to do is from t subtract this image of x over here. This is also trivial arithmetic. 2t squared minus t squared minus a squared. This is the result. And from here we construct the product. See, we have the integrand and the first differential. We know the first differential, we know the value of the function y itself. No need for any mind-boggling computation. Y dx, this is this result over here. Numerator is squared. In the denominator we have t squared times t cubed. 2 times 2 is 4, 1/4 factored out. We open up the parentheses again. This is the, in some sense, the trivial manifestation of the theory of integration of rational functions. So what do we have for our integral? 1/4 of y is there is t. Well, t squared raised to the second power will be t raised to the fourth power. T to the fourth divided by t to the third is t. Boom, game over. So we have our first sum. Next, there comes twice the product of t squared and a squared. T squared divided by t cubed. We have one copy of t in the denominator, and thus cometh the logarithm over here, right? See this guy and this guy. And now this is also trivial. We have the free floating summand, a squared squared a to the fourth power, a to the fourth divided by t to the third. And these integrals are trivial. Look at this. T squared over 2 minus a to the fourth divided by 2t squared by the rules of integration of these functions, right? So 1/2 we factor out, we get 1/8, and because we took 1/2 out, we multiply this by 2, 4. 4a squared, this is what? This is logarithm in base e of the absolute value of t minus, like I said before, a to the fourth over t squared. Game essentially over, problem solved. All we have to do is unwind our substitutions. And for the t from here, we also have right away what? T of x is x plus square root of x squared minus x squared. So here, if you experiment with the plus x, you will get a different expression. For x, you will have x with a minus sign. So once you do all the derivatives, you will get the minus in front. This is no big deal, nothing fundamental. And fundamentally difficult over here. So now we know this guy. The answer over here is known right away. We simply say 4a squared times the logarithm and base e of this here expression, absolute value. Game over. Now we just have to fight the tactical fight with this expression. Look at this, it's quite beautiful. T squared minus a to the fourth over t squared. And it seems over here, oh my, this is difficult. No, it is not. Look at this. This is x minus. This is, this is x plus. And this is what you will see in complex analysis. We're dealing with complex numbers all the time. We have 1 over x plus something. We multiply both sides by the conjugate. So this is plus, and this must be minus. See, I was trying to test if you're paying attention. Apparently you are. This is minus. Minus in the denominator, minus in the numerator. Here we manufacture a difference of squares. And what is the difference of squares? X squared minus x squared minus minus plus x squared cancel. Cancel. We have our difference divided by a squared. And that means what? The a fourth. Let's write it over here. The a raised to the fourth power times t squared. Let's write down what is the result if we know this over here. Well, it will be 1 over a raised to the fourth power, and then other a raised to the fourth power here, times x minus square root of x squared minus a squared and squared. And what do we have here? A to the fourth and a to the fourth cancel out. And now you should be able to carry out the remaining steps of this computation by yourself. A to the fourth t squared is this. All we have to do is take this result with the negative sign. In this result, I wrote it over here. T squared minus a raised to the fourth over t squared. It will be the difference of these two squares, x with a plus and then x minus. And it is evident, again, you do not need pen and paper for that. If you stare at this expression long enough, look at this. X squared and x squared minus sign cancel out. The square of this term minus the square of this term gone. And what is left? Minus twice the product. Minus times minus becomes a plus with the plus over here. Happy marriage. 4 copies of x times x squared minus a squared. And this is what we put over here with 1/8. 1/8 times 4 is x half times square root of x squared minus a squared minus this guy. 4 over 8 is what? Is again 1/2 of logarithm in base e. This is the absolute value. Let's not forget the sign, absolute value. Fundamentally, this is what we have, plus the silly constant of integration. And if we care to plot this derivative, I showed it in blue over here. It will be some funky curve that will go this way, and the second branch will go this way. Again, this derivative is defined precisely on the same union of two subsets of real numbers. And if we define the integral in such a way that when x is equal to a, then the integral is equal to a. So, for example, if we say if x is equal to a, then the integral is equal to a, then from here we will have what? Our constant of integration c. In this case will be equal to what? 0 gone, 0 gone. This will be x equal to a with the minus sign, so constant of integration will be a squared over 2 times logarithm of absolute value of a. Keep in mind this constant, we'll come back to it in a second, but now that you understand how this computation unfolded, you will also recall that when we stated this problem, we required at least 2 creative ways of evaluating this here integral, this one way counts for the first solution, and this justifies the title of this episode as hyperbolically speaking. And in the second segment that you will see in the second segment, you will see in a second, we will capitalize precisely on the fact that our integrand can be expressed in this particular shape. For our second creative solution of the given problem, we will capitalize on the fact that the given integrand y can be squared on both sides, and we obtain y squared equals difference of squares, x squared minus x squared. From here, we rearrange this equation as follows. We carry y squared to the right-hand side and a squared to the left-hand side. We obtain this equation over here, and then if we divide both sides of this equation by a squared, we obtain this equation over here, which looks somewhat silly, but this is reminiscent. Again, this comes from analytic geometry, where you will be shown that in the as a canonical representation in the Cartesian coordinate system, the equation of a parabola can be expressed as follows: x squared over a squared minus y squared over b squared equals 1. If minus is replaced with the plus, then what do we get? We get an ellipse. But this is a different story. Here we want to loiter around this particular shape, and again, we want to use what I refer to as an Eulerian observation, because Leonard Euler, the Swiss-born mathematician, was an absolute master craftsman of taking some childish observation, but then spinning that childish observation creatively 7 ways to Sunday into something that's not childish at all, something that's not trivial, but something that is meaningful and deep. And 200 years later, we keep discovering more and more of Euler's wonderful ideas. So here we take this expression, we take the left-hand side to be the difference of squares, and we factor it as follows in predictable way. Again, this is middle school arithmetic, duh, but here is the idea again, that behind each and every symbolic shuffling or algebraic computation, there better be or should be a sound mathematical idea that we generated when we were thinking like a mathematician. The way mathematics works, you're pretty much guaranteed to fail. Failure is not an option, in the sense that failure is pretty much a guarantee, and this is where your intellectual stamina will form and manifest itself. Fail, try again, fail, try again, fail, try again, until you succeed. So here the idea is the following: how can we represent these two functions over here, the sum and the difference, in such a way that when these two functions are parameters of t, let's say our favorite real number t, then their product again folds back into a square or into 1, as it were. Well, perhaps because this is a pronounced multiplicative relationship, perhaps one of the simplest ideas that will come to anyone's mind is to pick precisely this: a over t and a times t when they are multiplied. Unlike Quaternions, real numbers commute under multiplication. Here we can shuffle the numbers any which way you want, and you will engage in this exercise in the theory of groups when you will be manipulating the generators of a group. You will show that if all the generators of a group commute, then the group is commutative, and precisely that, by commuting the generators, you will bunch them up into like piles: a squared b to the 4th times c to the 17th power, or what have you, and then you will manipulate this idea into submission. But here the product folds into a squared precisely. So what will this entail? Well, if x minus y is a over t and the sum is a times t, then adding these two equations together wipes out a, creates 2 copies of x, and then x is equal to this expression. And then if, let's take a look, from this equation we subtract this one, then this will wipe out x, but double the quantity of y, and then y will be expressed as t minus 1 over t. And again, this is our idea. Why did we want to split? Why did we want to factor our integrand into this particular shape? Well, again, the idea is the same: to create some sort of guarantee. Ideally, if we can have it, we will take it, but to create some sort of guarantee or some sort of an industrial strength method that will theoretically less so in a large class of functions in such a way that after the set substitution that we obtain through clever factoring, we will be able to compute the underlying integral in closed form as a finite combination of elementary functions. For example, over here, instead of a over t and a times t, can we take something as wild as, I don't know, cube root of arctan of 1 over x, or 1 over t, for example? Can we take this expression? So we take this guy for one expression and it's reciprocal for the other. Yes, of course we can. When we multiply two such quantities, they will annihilate each other. They will become the multiplicative identity 1, and all is good. But the question is, what will we gain by such a wild substitution? Will we be able to guarantee that no matter what happens, we will be able to integrate the result in closed form? The answer, of course, most likely no. These wild integrals are just that, wild integrals, and most of the time they are not integrable in closed form. So this is precisely the idea of this maneuver. Factor, but then substitute with functions that are rational in t in such a way that, look at this, x is a function that is rational in t, again coming back to the idea from the previous segment, and y is a function that is rational in t. And now instantly we have what? The first differential from here, 1 minus 1 over t squared, and then times dt. And then from here, instantly it follows what? Square root of the given material times dx. This is y dx. We have y. So we put this, factor one copy of t, 1 minus 1 over t squared. So this is what we have, t times 1 minus 1 over t squared squared. Open up the parentheses, push t through, and look at this. We have precisely, or almost precisely, the integrand that we had a few seconds ago in the previous segment, where we arrived at that particular shape through a different reasoning. Here our reasoning was quite different. We did capitalize on the fact that we're dealing with a certain hyperbola, but we executed a different maneuver. And now the rest is just, again, middle school arithmetic. T squared over 2 logarithm of the absolute value of t minus 1 over 2t squared minus 1 over 2t squared. This is the result. The log t, how do we know log t this time? How would we reverse engineer our substitution? Yes, again, a little bit of symbolic shuffling. Multiply this, both sides of this relation, by reciprocal of a over 2. 2x over a equals t plus 1 over t. Multiply this equality through by t. So we have the quadratic equation in t squared minus 2x over a times t plus 1. Compute the roots nicely, things square nicely, and this is what we have, x over a plus minus square root of x squared divided by a squared minus 1. Again, across two roots, we want to pick the right one, plus or minus. Invented an algebraic reasoning for why we should pick this or that root. Evidently, we may pick the top sign over here, and the game is over. Once we compute again t squared minus 1 over 2t squared, here is 2 also, don't forget, then the guarantee is that the most of the material will cancel out and we'll only have what we need as a leftover. I will not bother you with these details, because the real idea behind this maneuver of factoring the given integrand and then substituting into something that is rational in the new parameter is the following. Since we're dealing with the hyperbolic function over here, in the next segment we will exercise a little bit different idea. Here, instead of t, we will take e, the base of the natural logarithm, raised to the negative t, and here we will take e raised to the positive power of t. Here we'll reuse the same factorization of our integrand as the product of the difference and the sum, but this time we will put the difference equal to a times e, the base of the natural logarithm, raised to the power negative t, and the sum is the same thing, but this time the exponent of t is positive again. through the summation and the subtraction, we obtain this here expression for the function of x as t, and here the expression for y is a function of t. Some of our viewers may recognize what these functions are. This is the so-called hyperbolic cosine, the hyperbolic sine, and I will say a few words about these functions in a second. But if we carry out this computation through, again, the motivation is not to just go on a wild goose chase and pick any random function, but again, we want to, what is the goal, the end goal of our exercise that we're doing here? The end goal of what we're doing is to come up with such a representation of the variable x and the corresponding function y that the result will be integrable in closed form. Hopefully we can come up with a rational function here. The function is rational not in t, but in e raised to the power of t. Why is that? Well, if all the material, everything, by the time we unwind all our substitution, everything is expressed as a combination of this here or this here material, then we simply put, where can I use it? Let's say over here, we simply put e raised to the power of t as a new variable. Let's say u, then du is equal to e to the power of t dt, but e is u, so du over u is equal to dt. The rest of the material becomes u. Again, we come back to the rational function and the game is over in some sense. So here, once we have this result on the books, or this idea on the books, the first differential is given instantly. And look at this. What is this? This is actually the function to which we refer as y. So dx over y is dt, or dx equals y dt. And that means instantly that this expression is y dx. We have it. We have our differential as the difference. Our function here, y, is also the difference. Squared, we get e raised to the power 2t minus their product, 2 plus the square of the last term minus 2t. And again, the game is over. This is where we win. We know how to integrate this material. This is trivial business, and I wrote the result over here, a squared over 4. Then this will be 1/2 of the exponent minus 2 times t minus 1/2 of the negative exponent. Pay attention over here, there was plus, because this is minus, it's percolated into the answer as a minus. Game over. So now we just have to flip back, reverse transform. Remember the transform and conquer problem solving approach, of which integration is a grand exercise. Find a clever transformation, solve the simple problem, reverse transform, reverse substitute. So how do we find the reverse substitution? Well, admittedly, a little bit of middle school algebra over here. We put e raised to the power of t is z, and then we come back to the equation that we solved a few seconds ago in the previous segment. This is our favorite quadratic equation. 2 roots. Out of 2 roots, we pick 1. In this case, for example, my reasoning was that e raised to the power of t is always positive. Look at this. Its graph goes like this. It never even comes close to 0. So for that reason, I picked the plus sign over here. Take the logarithm of both sides. Logarithm of x plus the square root minus log of absolute value of a. We use the property of logarithms. And now we have from a squared over 4, we have 2 over here, 2 in the numerator, 4 in the denominator. 2 in the denominator sticks. A squared over 2 log x plus a squared over 2 log absolute value of a. Don't forget, we have this term and we have minus this term over here. So we bring it in. And lastly, when the students see this expression over here, we need to take care of this combined with this 1/2 we don't care about. It's the square of this exponent minus square of this exponent. How do we manufacture it? Well, again, it's a trivial business. Once we successfully generated a good idea, or we thought as a mathematician, x times y, from here, look at this, x times y instantly gives us a plus b times a minus b, difference of squares. We instantly have our result. So this here animal is 4 over x, a squared times x times y. And what is y? Well, y is our favorite square root. You see that this is our result. That's it, game over. Since we have 4 over a squared as a factor of this material over here, it will cancel out with a squared over 4 over here, and we still have 1/2 and 1/2. That's it, game over. And we can write down our result, 1/2 of x times the square root. This comes from here, x times y. You recognize the square root as y. This is where the ease of manipulation, perceived ease of manipulation, comes from, plus our logarithm, this and that, plus we have another constant of integration, c prime. And what is this c prime business? Well, again, if we define our integral in such a way that it vanishes when x is equal to 0, which is a sensible thing to do, look at this. 0, 0, a squared over 2 with the minus sign log a, plus a squared over 2 log a. So that means that basically in this case, under this definition, we can put c prime is identically equal to 0, and the game is over, problem solved. We have our result. Again, logarithms can be expressed through the inverse trigonometric function of arctangent. This is another way to show the result and deal with the consequences there. But why did I bring your attention to this particular observation? Well, I brought your attention to this particular observation because, again, since we're dealing with the hyperbola and we see that essentially hyperbolic functions rationalize the given integrand and allow us to perform basically a baby style integration that is less than trivial, we win. Here is the thing. It turns out that it is here we let's say we manufactured this idea in some sense by our will, but it turns out that it is possible to define the hyperbolic functions. Let's say the hyperbolic cosine, the hyperbolic sine, the hyperbolic tangent, and hyperbolic cotangent. These 4 basic functions, it is possible to define them by a direct analogy with circular trigonometric functions. In other words, in the same way we use our origin center unit circle to define cosine, sine, tangent, and cotangent, in exactly the same way it can be shown, and I will show it in the upcoming episode, that the hyperbolic functions can be defined, except then for a clean definition or a clean deduction, we will not be guessing in some sense at these two or taking them as preconceived knowledge, because some students may sometime in their middle school, high school, or early in college heard something about unit hyperbola, hyperbolic functions, and they can say, let me try this. And they may converge on a successful deduction and a successful computation, but in the definition, in the deduction for the corresponding functions shown over here, hyperbolic functions, we will not be taking this as a guess, but we will be deducing this to relation, this one and this one, and we will be proving that under certain assumptions, if we take the way we define circular trigonometric functions as a template, and then onto the template we drop our unit or rectangular hyperbola, then these definitions follow necessarily. And when we will be doing that, we will be computing the corresponding integrals, and in that case, in some textbooks, the computation of the underlying integrals that will be carried out will be done as follows. One more time, when we will be discovering / defining the hyperbolic functions by analogy with how the circular trigonometric functions are defined, we will not be taking any guesses, but we will be deducing with the inevitability, with the mathematical steamroller, that if this and that is happening in the circular trigonometric functions, then by direct analogy, such and such is happening with the hyperbolic functions. And while we'll be doing that, we'll be computing an integral. And here is another way to compute this integral. do the integration by parts once, taking the square root as u dx dv. That means that v is x. The product of uv minus v du, the differential of the square root, will have 1/2 in the denominator, the derivative of x squared. This is a composite function, 2 cancels out, so we have x squared in the numerator with our differential and the square root in the denominator. But here we will do plus and minus a square. This is adding 0, nothing bad is happening over here as I depicted here. So by taking this term, we manufacture what? We manufacture our integral. Again, here we have the integral a, where the square root in the denominator is squared by scaled by the a squared. So we have the equation. Carry the integral to the left-hand side and obtain 2a is equal to this. You see, so we have our product. When we compute I, it will be x divided by 2. And this integral j, again, you see, we should not be computing it with the hyperbolic substitution, even though we know too well that it will work. But in order to avoid circular reasoning and present a clean deduction / discovery, we will be evaluating this integral using our substitution over here. Let me highlight it in yellow for you. This is our substitution. You know what it is. Hyperbola, straight lines parallel to the asymptote. And t in this case is not an angular coefficient, but simply a number that offsets these parallel lines, straight lines parallel to the asymptotes. And the game is over. From the previous segments, you remember these relationships. Once you inject them over here, you will see that the difference of squares and difference in squares cancel out. 2t, 2t cancel out. And here we have our favorite trivial integral dt over t. Game over. Natural logarithm in base e, absolute value of t, and we know what t is. From here, t is instantly x plus the square. Boom. Game over. We have our logarithm divided by 2, scaled by a square. Game over for a nice, clean deduction of the definition of the hyperbolic functions by a direct analogy with the circular or traditional classical trigonometric functions. Now, this is it for this problem, and we will move on to a new challenge next. Wonderful. Now that you've been professionally instructed, so to speak, about the idea that behind every algebraic manipulation there should be at least one, preferably more, sound mathematical ideas which you generated when you were thinking like a mathematician, our next challenge will be a problem in mathematics S3M18, the problem number 18 for season 3, and the objective of this problem is to evaluate again the definite Riemann integrals between the boundaries of 0 and pi over 2, 0 and pi over 2 in both cases, for the trigonometric function of sine and the trigonometric function of cosine raised to an integral power positive in general. The most interesting case, the positive integral power. We're interested in the cases of m equal to 1, 2, 3, 4, 5, 6, 7. And of course, the first two cases, 0 and 1, are trivial, not interesting. We're interested when the value of the variable m grows significantly into 2, 3, 4, 5, 6, 7, and so on. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S3M18.